In this video, we're going to learn about mathematical induction, and in particular, induction with series and sequences. So this can be a bit tricky to get your head around at first, but once you've done a few examples, it makes a lot of sense what we're doing here. Basically, induction is a way to prove a statement for every possible value of that statement. So we've got a statement like this here, which is saying that this sum on the left is equal to this thing on the right. Now, let's just work out essentially what this is on the left and the right and make sure this statement makes sense. So here I'm going to have sum I equals 1 to n of I. Here I'm going to have n plus 1 over 2. And we'll try it for a few different n values. So let's try it for n equals 1 first. For n equals 1, the sum on the left is I equals 1 to 1 of I, which is, well, 1. On the right, you've got n is 1, so you're going to get 1 bracket 1 plus 1 over 2, which is 1 times 2 over 2, which does work out to be 1 as well. So is the statement true for n equals 1? Yes. So what we do is we say that P1 is true. And usually what you do is you say let Pn be the statement that the sum I equals 1 to n of I equals n plus 1 over 2. So this is the statement we're trying to prove, and we've proved that it's true if n equals 1. So that's good. Basically what we're going to try and do is prove that it's true for all n values. Now, usually when you do an induction proof, you don't have to check n equals 2 or 3 or 4, but let's just do this to make sure we're on the right track. So this is I equals 1 to 2 of I. So this is going to be 1 plus 2, which is 3. On the right hand side, you've got n bracket n plus 1. So that's 2 brackets 2 plus 1 over 2, which is 2 times 3 over 2, which is 3. I'll reiterate, if you're not comfortable with summation notation, this thing just means like 1 plus 2 plus 3 all the way up to n. That's what we're doing. Okay, so it looks like it's true for n equals 2. I might just show one more so we have an example. N equals 3. So you got I equals 1 to 3 of I, which is 1 plus 2 plus 3, which is 6. Then on the right hand side, you've got 3 plus 1 over 2, which is 3 times 4 over 2, which is 6. So yep, P2 is true. P3 is true. Now we'll stress again, when you do an actual induction proof, you only need to check P1 is true. So induction proofs sort of have 3 steps. So basically the step 1 is going to be to check P1 true, which we've done. Step 2 is to assume PK is true. And step 3, use this to prove PK plus 1 is true. So the step 2 and step 3 sound a bit weird, but I like to use an analogy of like dominoes. So you've got a whole bunch of dominoes that you're trying to knock over, and you can imagine knocking over a domino would be like proving a statement. So this is P1, which we've knocked over. This is P2 and P3, which we've knocked over. We proved those. But we want to prove it all the way up to P infinity, basically. So what you do is you just take any domino, PK. K could be any number. And what we want to prove is if PK knocked over, then PK plus 1 gets knocked over. And if you've ever like set up a bunch of dominoes, you'll know that, well, this would cause the whole stack to knock over. Because if we have these two things being true, then if we have P1 being true, then this statement here would make sure P2 gets knocked over. Then P2 is true, so P3 gets knocked over. Then P4, then P5, all the way up to P infinity. So that is how we're going to prove it. So we're going to take step 2 here. Assume PK is true. Therefore, and we'll write out what that means, I equals 1 to K of I equals K plus 1 over 2. Now, you'll notice that this statement is exactly the same. Exactly the same as this Pn statement here, only you've just got K instead of N. That's just always what you do. All right, so step 3 will be to prove that PK plus 1 is true. So when we do this step, I always do like a want to show. What do we want to show? So I want to show essentially this statement here, but with K plus 1 instead of K. So that I equals 1 to K plus 1 of I equals K plus 1 plus 1 over 2. That's what we want to show. So let's try and do it. We're going to start from this left-hand side. So we're going to go I equals 1 to K plus 1 of I. And then pretty much what you always do is you split it. So like that. You split it up to the first K terms, and then you have your next term. So this is going to be the sum I equals 1 to K of I plus, and then this next bit is just going to be K plus 1, essentially. And if we think about what this thing is, then we can compare it to the statement that we've assumed is true, which is this. So we can replace this sum with the K bracket K plus 1 over 2 because we've assumed that's true. So you always use your assumptions. K plus 1 over 2 plus K plus 1. And now we just simplify this. What we're trying to get is this thing on the right here. So hopefully we can do that. So probably the easiest way is if we shouldn't expand the top because, well, it looks like the top's factorized in what we want to show. So maybe if we cross multiply, so essentially I can take this thing here and times it by 2 over 2. So I get K bracket K plus 1 over 2 plus 2K plus 1 over 2. And the reason we do that is now we can write everything over 2. Then we could look for common factors here. Common factor here is K plus 1. And what am I left with? I'm left with K plus 2 over 2. And that looks almost like what we want to show because that thing there is just K plus 2. So it looks like we've done it. So you say a couple things. Therefore, PK plus 1 is true. Therefore, Pn is true for all n greater than or equal to 1, where n is an integer, by mathematical induction. Now, I have no illusion that this is not easy. So we're going to do a lot of practice of this now and also at the start of next year. So there'll be plenty of time to get used to it. Basically, what I might do is do an alternate proof of this one, but not using summation notation. But I'll do that at the end of the video just so you can see what that looks like. So next thing it wants us to do is find this sum. So I equals 1 to 100 of I. Well, we can just plug in 100 times 101 over 2 using our formula, which I think gives you 50-50, something like that. If you've noticed, this is actually just an arithmetic series. So induction is a way that you could prove the formula for an arithmetic series, which is pretty cool. Okay, so the video is over now. So if you did understand that summation proof, don't feel like you have to keep watching, but I will prove it using just not summation stuff. So Pn would be the statement 1 plus 2 plus all the way up to n equals n plus 1 over 2. So this is not summation. It's using like the dot 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 notation. And you can see that's equivalent to what they're asking us to prove here. So basically step 1 is going to be to prove that P1 is true. So on the left hand side I get 1, and on the right hand side I get 1 plus 1 over 2, which is 1. So that's really good. So P1 is true. Step 2, assume pk is true. Therefore 1 plus 2 plus k equals k plus 1 over 2. And usually I'll label this with a star. Step 3, prove pk plus 1. So what do I want to show? Want to show that 1 plus 2 plus k plus 1 equals k plus 1 plus 1 over 2. So here's how we do it. We start from the left hand side. 1 plus 2 plus k plus 1. This should all equal. Now we split it off into all the way up to k. And we know this stuff equals k bracket k plus 1 plus over 2. Using star plus, and then there's k plus 1 on the end. And then from here it goes pretty much exactly like our last induction went. K plus 1 over 2 plus 2k plus 1 over 2. Then we write all k plus 1 plus 2k plus 1 over 2. We pull out our common factor of k plus 1. And we're done. Therefore pk plus 1 is true. Therefore by induction we have 1 plus 2 plus n equals n plus 1 over 2 for all n greater than 1 and in C.